answer sheet, the white paper that we give you. Yes?
Was the final in this room?
Final is in this room, Friday, 7:45, am I correct? 2 hours. 2 hours. Other questions regarding the final? Okay, so let's get started. So this problem of a water jet is very simple. Let me first define the problem. So it's a fairly straightforward problem. I have a water cannon at point O, which is happen to be 40 feet horizontally from a building, and 50 feet, I showed that wrong. So the origin point O starts from the exit of this water jet. And you are told the velocity of the jet is 100 feet per second. It's 40 feet horizontally from a building and 50 feet height from the top of the building. What I want to know is what orientation, angle theta of the water cannon that will allow me to clear the point A. And upon doing that, I also want to find out the velocity at that point A. What does that remind you of? A problem that you're very familiar with in your prior classes? Anyone? Projectile, dynamic, particle dynamic. It turns out in some of the rare cases, fluid mechanics behave almost just like a dynamic problem. So this is almost no different than a cannon shooting a projectile that's required to clear that building corner A. And from your particle dynamic, can anyone tell me how many answers do you expect? A trajectory that will clear the point A? There are two. One is a sketch. We have a theta mean and a theta max. The second one will be a higher angle where on the path down, the water jet will also clear that corner A. So that is the setup for the problem. And a couple of assumptions will be needed to make this problem trackable in terms of fluid dynamic. So first, you should all know this is a gravity-driven problem from your particle dynamics. If there's no acceleration due to gravity, there's no problem. The cannon will go on infinitely without stopping. And for analysis, I'm going to establish a coordinate system. Origin is shown. X, typical horizontal. Instead of calling the vertical axis y, I'm going to call it z. That's the upward coordinate. So I have xz coordinate as shown. For fluid, and just like you did with your particle dynamic, you make frictionless assumption, and we'll do the same likewise in this water jet problem. So with that, I have solved the problem. Question is, how do we proceed to solve for it? First, let me stop and make sure you understand the problem statement. Very simple, almost particle dynamic, except instead of projectile, I'm replacing that with a steady, continuous, steady, I should mention that. Continuous stream of water, and I can visualize and convince myself that this continuous stream is almost like a streamline, that it doesn't break. Now in reality, you know that the water jet starts to break up and kind of splashes, but we're not going to look at that in such detail. We just assume a steady stream of water jet continuously clearing the corner A. It's an assumption, it's first order, but it's sufficient enough for us to get the angle theta mean and theta max. So that's the step of the problem. Do you understand the physics and the requirement? What is it that we're trying to solve? Any questions? So let me review for you the particle dynamic part, and I will do that quick because it's mostly from your, and I'll call that part A, that has almost, it's exclusively dealing with a projectile or particle dynamic. For that, I have two equations of motion in the two directions of interest, x and z. I want you to tell me what is the equation of motion in the x direction. What can you tell me about x is cosine theta of the velocity v sub 0, 100 feet per second, with the component parallel to the x-axis. That's the x direction velocity. From your particle dynamics, what can you tell me about this velocity component? Yes? Say it again?
Cosine theta times t equal to distance traveled.
Yeah, that's correct, but the more first insight is this velocity in the x direction is what?
Constant.
It's a constant. It's a constant. What you say is correct. You know, I can use that to calculate the distance by multiplying the velocity by time, but the more important immediate observation first and foremost is that horizontal velocity is constant. As such, I can get the distance x as a function of time. Very good, but yeah, that's the part that I think you need to remember. Now the z direction is more complicated. I'll give you the answer. I won't divide that. It turns out in terms of time, the z direction is a parabola, just like a sketch. And this equation of motion is dictated by gravity g. Anyone want to make a guess if I ask you to derive this from first principle, what will you start with? This is an equation that some of you may remember, most of you don't. For those who may not remember, if you have to derive that from first principle, where will you start? Where will you start? Anyone? Kinematic? What about kinematic? It's actually dynamic, because we do involve the gravity or force. Let me give you the answer. You can say that it's dynamic too. I will not argue with that. And the fact is, or kinematic, the fact is the acceleration g, which is negative because it's opposite to the z direction, is my acceleration. And acceleration is simply in the z direction, the vertical velocity, divided or differentiated with respect to time. This is your starting point. And what you do is integrate that twice to get finally the distance versus time squared. And the integral constants, the two, can be determined by the boundary condition or so-called initial condition. So I won't go through that. Those just dot, dot, dot. and something you can do on the back of an envelope and quickly get to the answer. So with the two equations I show you, I'm going to combine them such that I can eliminate the unknown that I don't care for, which is t. The resulting equation which is a function of the z coordinate being that of x, is like I said before, is a parabola also. And hence, any particle dynamic, including this simplified water jet, will follow a parabolic track. And this is no different than what you have done if you assume this is a cannonball. Questions? So with that, I can now substitute to the stated problem where the velocity is 100 feet per second. And at point A, my coordinate is 50 feet vertically and 40 feet horizontally. So I have now one equation in terms of x and z, which I've known both from the problem statement. I have the initial velocity. I have now solved for the angle theta, and it turns out when you substitute all the values, you require trial and error or iteration to get to the final answer. So let me substitute those values in to show you what the final equation looks like. So this is copying all the numerical value to the problem at hand. If you simplify this, with all the numerical value calculated, I have now an equation all in terms of theta. However, it's tangent and cosine square is not an explicit equation I can directly calculate for theta. The only way you can get to the answer is by guessing. Take a value of theta, 5 degrees, put it in the left-hand side and the right-hand side, see if they equal. If they don't, go to 10 degrees, 15, so on and so forth, until you get to the answer. And it turns out there are two angles, like we expected, that will meet the requirement. The maximum angle of almost 90 degrees, 86, and the minimum angle of 55 degrees. Both will satisfy the problem, like we sketched before. One go to a higher peak, the other one just go further horizontally. So let me stop here and see if you can understand this problem from the viewpoint of fluid dynamics. Very similar to what you see in particle dynamics. Any questions? Yes?
So if we say that the velocity in the z direction is changing, how is that still steady? Or if the velocity in the z direction is changing with time?
It's steady in terms of all the velocity. Yeah, that's a fair question. How should I answer that? It's steady in terms of this trajectory is not changing in time, right? It's a steady streamline, and it's not changing in time at all.
Does continuity still apply?
Continuity still apply, but it's a little bit different, and I don't want to touch on that. Yeah, continues to apply. Very good question. Yeah.
So would like the diameter of the.
Jet will change. That's correct. Very good observation. Yeah. Other questions? Other questions? Okay, so the last part is where I want to calculate the velocity at point A, and that we choose to do it by the Bernoulli equation. Because it met all the requirements. And I will apply Bernoulli along the streamline from the exit of the jet to point A. And here you can help me to simplify the equation, and I also want to make a very subtle point about the velocity. It's an open water jet. And this is something you need to always remember, so I should. What does that mean to you in terms of the pressure within the jet? It's atmospheric. Pressure is PA everywhere within the jet, no matter at what location you are along the jet. That's what we meant by open water jet. So with that, what can you tell me about P0 and P2? They're both PA and can be taken up. Questions? The velocity at 2, V2, what velocity is that? VC, Vx, or V total? This is the trick part. Let me ask that question one more time. Velocity at 2, as well as at 0, at the origin of the jet, is it the velocity in the x direction?
Where is
2, sorry, is the same as 8. Thank you. Yeah, I just used the more general nomenclature, and now we're going to change it to 8 momentarily. So 2 can be any point along the water jet, as I stated now. Doesn't have to be point A, can be anywhere along the water jet. All right? So I have my question now for the Bernoulli equation for the velocity in the Bernoulli equation. Is this velocity V0 or V2 only in the x direction, or only in the z direction, or the total velocity? Total, very good. Should be very definitively total, because in the Bernoulli equation, we integrate the Euler's equation of which the velocity is the total velocity. So with that, then, and apply that to point A. What I have then is simplifying the equation at 0, the origin, I have 100 feet per second. The origin is chosen by convenient at the exit of the jet, so z is 0. 2 now become point A. The height z is 50 feet. So now I have this equation with the only unknown left. I'm missing a term here of VA squared, so that you can solve for VA. And it's about 82 feet per second. So the velocity have changed. Start from 100 feet per second at the base, where clear point A, it become less due to gravity. And as the point being made earlier, because the velocity is changing, the air of the jet actually from continuity is also changing. Question on that? Yes?
You could get the same answer if you found, because you have a term over here for what the x velocity doesn't change, and you have a way of finding the z velocity. So you could
Absolutely.
just do like the triangle.
You can get the velocity upon A from purely particle dynamics on the right side of the board. This is just to tie in the whole big picture of Bernoulli, how it can apply to a water jet, and specifically in preparation for potentially PE exam problem. That's quite common, and it's very doable a problem as you apply Bernoulli, just like we did, but you get the same answer. Questions on this last part? That is something I didn't cover in the Bernoulli session, but it's also timely to cover that now. Questions on this? Yes?
You have like a no-slip boundary condition.
Yes.
You talk about like fluids flowing over solids.
Mm-hmm.
How does that relate when you have two fluids? Like you have water going through air here. So if we were to consider there to be like some friction, how does that differ?
That is no longer what we call a low-slip boundary condition,
Right.
because when the air and water are at this common interface, both can be shielded.
Right.
So the low-slip boundary condition will not apply.
Okay.
More information will be given to me in order to solve that problem, right? So fluid interaction is a little bit different kind of worm that we are not prepared to discuss in detail, right? Other questions? So at the peak here, what is the vertical velocity?
Zero.
The peak here over here. What is Vz? It's zero. Yeah, just like particle dynamics. Okay, other questions? Yes?
Is that a trial and error for the tangent one? Can we just convert cosine squared, 1 over cosine squared to secant squared, which is like,
No matter how you use trigonometry to convert that, you still end up with an equation that cannot explicitly solve for in terms of an angle theta, no matter how you do it.
but is it cosine squared, 1 cosine squared and that 1 plus tangent squared, and then you have everything comes to tangent?
Yeah, based on the denominator, it's not apparent that you can do it that way. Yeah, it's just because you have a cosine square and then a tangent, it just doesn't lend itself to an explicit solution. Right? Try and error is the only way you can get to the answer. All right? Other questions on this? Okay, so let me shift here to the homework problem due today. Very quickly, there's not much to it. I didn't talk about the continuity equation. This kind of fully developed flow is very simple because the fact is fully developed. The conclusion from continuity, I hope all of you see it when you apply the boundary condition, is that the V velocity is also zero everywhere, not just on the solid surfaces. Anyone who has not been able to come to this conclusion, you need that to finish the second part, of which you will have to simplify the momentum equation of Navier-Stokes in the x direction. There's gravity, but there's nothing in the x direction, so that's zero. You are told it's no pressure gradient in this problem. That's also zero. On the right-hand side, steady, fully developed, FD, fully developed, and the velocity V is zero. So it's practically right-hand side is all nothing but zero. The other term that can be dropped, also because of fully developed assumption, is the term on the left. So what left behind is a very simple differential equation that you can solve. And it's a linear velocity with respect to the distance y, and the two boundary conditions, the lower wall and upper wall, will get you to the answer. Yes?
the problem statement, how do we determine that's the null?
It's not clear. I think in the class lecture I told you, because it's infinite. The problem stated only this: infinite parallel plate, meaning it extends infinitely towards the wall and also infinitely towards the window. Right? Because of this condition of the problem, the only way that the flow can be established within this infinite plate is that they are not changing in any of the direction with respect to x, and hence it's fully developed. It's not clear, so in the lecture, I make sure I mention that, so you can, well, assume it's a little bit presumptuous. You should be able to, at this point, for the fact that it's an infinite plate, is so big that it's not changing in the x direction. Yes?
So if there's an infinite plate with the two speeds not not constant, would it still be fully developed?
Yes.
Say that one of them was speeding up?
Yes. You still think about the way they move. Away from the edge, if you are in the center of the plate, all that region near the center is all fully developed, even though they're different velocity. Fair question, but it can be established. Right. Other questions on this several problem that relate to the use of the Navier-Stokes equation? The only thing left is to look at how we may get a PhD by making some very clever assumption on the Navier-Stokes equation. So let's go through that part, last part of the formal lecture, and beyond that is all nothing but review. So this handout called boundary layer analysis 2A was the PhD thesis. Obviously, this is a long time ago. Due to BASIS in Germany, and I told you a month ago at the dawn of World War II, Professor Pantos had a team of graduate students working with studying the boundary layer of fluid mechanics, and that's well before we have computer or even calculator. So everything has been done by slide rule, if you know what that is, or pencil and papers. And what we are asked to look at is now a laminar, always, because turbulent require alternation of the Navier-Stokes equation. And we are looking at the laminar boundary layer on a plate, an infinite plate. XY coordinates shown, the dashed line represents the edge of the boundary layer. Now this is very critical because the flow is always continuous from leading edge to trailing edge. This is never a fully developed flow, simply for the fact it's not confined, it's not internal flow. The boundary layer will continue to grow as the plate gets longer and longer and longer. And because of that distinction, this is not a fully developed flow, and hence a lot of the simplification we did with the homework, that anything with respect to x, the derivative is 0, is no longer true. Just that small subtlety makes this problem a whole lot more challenging and difficult. So we're going to get gravity, just to make the problem simple. So it may be just for air, and it's steady state. And it's also incompressible. All those are attempts to make the equation more trackable. Here's one very important given condition. We were told as a problem statement, we are dealing with a boundary layer growth where there's no pressure gradient in the x direction. In the x direction. So that's the problem statement. Seems pretty simple and innocent, but it turns out there's a trick one can use to help get to the final answer, and that's the formula you have used for some of the prior homework for boundary layer estimate. Do you understand the problem statement? Do you understand the difference between this, which is not fully developed, versus several of your homework, which is internal flow confined by two parallel plates that led to a fully developed flow? There's a very important subtlety between them. And it will not allow you to simplify the Navier-Stokes equation as nicely as we have done before. Any question before I start? So how would you analyze this problem? What two equations will you use? So what are we after? What do you want at the end of doing the analysis? What is it that you are trying to calculate? Anyone?
Description of boundary layer.
Description of the boundary layer, in this case, is the velocity u, which is the velocity in the x direction as a function of the coordinate y. And more specifically, so I want this to be calculated, and then once I have that, what's the next more important thing that you also want to know so that you can estimate some drag due to the flow of viscous effect on this plate? Anyone? You want the shear stress. Remember when we, way back for problem 9, you were given this formula for shear stress as well as the boundary layer thickness. We are now coming back to fill in that gap. So back then, these two formulae were given to you, and you were told just to use it without worrying about how it comes about. Now we're going to finish the semester by looking at how we close the loop. These two formulae, you have used it for several of your homework to estimate the shear or frictional effect on the plates, on the car hood, and estimate the thickness of those boundary layers. For very simple problems, zero pressure gradient, but at least it whets your appetite. Real problems are a whole lot more sophisticated than that, but at least that's the framework of which we will build on more complicated problems. So this is what I'm attempting to do, is to fill in that missing gap. How does those formulae come about? Starting from this problem statement. So this is the final exam, and I ask you, how would you start this analysis? Just tell me your approach. What will you do? What will you tell me? What equation will you use? I want to hear it in the order I want to hear. Continuity. Really, this is, seems very daunting, but it's just the same old, same old. So you use continuity, and then the next one? What else would you use? Do you want to use Bernoulli?
No.
Why not? Viscous, there's friction. I cannot touch Bernoulli, or I'll get burned. Right, no Bernoulli. So what else will be needed? Momentum. Momentum, same old, same old. Momentum, except now you have to account for viscous effect. You cannot quite do a control volume analysis like we did before. You need to apply a differential analysis of momentum. That's the Navier-Stokes equation. That's the roadmap. If you can say those two things, you get full credit. You know how to solve it. But do you understand the foundation of what I'm trying to stress? Questions? The rest is detail. But at least you should be capable of telling me how you approach the problem. Continuity and momentum. No Bernoulli. Okay? Questions? So let's start with continuity. And I'd like to at least have you be able to simplify the equation for me. Just like you did with some of the homework, except now it's not a fully developed flow, so it put a whole new dimension to the problem. So continuity in 2D, by the way, this is all in your handout. It's no point for you to copy. I start with the general 3D equation, and from that we can see how you can help me to simplify that. Just pretend you are Professor Bassis, and now you're trying to obtain a PhD in fluid. So simplification? Anyone quick?
EDX is a constant.
This is 0. Tell me why. There are two different reasons. Both are valid. Steady state or incompressible. Very good. What else? Quick. 2D.
Last term.
You were told it's a 2D problem. Last term is 0 because there's nothing into and out of the board. So now, the remaining equation, the only thing you can do is to factor out the density. And unlike your homework, which is a internal confined flow and fully developed, this is not the case here. This is a boundary layer, external flow, and the V velocity is not zero, and continuity will stop right here. You cannot simplify that any further. Do you get it? Do you agree? This is different from your homework, and that's why I want to spend the time to walk you through that. The momentum equation in the x direction is the only one that we care. And I will copy that down in the 3D formulation and start asking you to help me to simplify that. So this is the 3D Navier-Stokes equation that accounts for viscous effect. Now tell me how you will simplify it based on many of the lessons you learned from your homework. Starting from left, marching down to the right.
0.
0 for what?
Gx.
Gx is 0. Very good. Because the gravity is only vertical in the y direction, and I don't care. dp dx. Why? Because I said so. Very good. This is a very important reminder. 0 pressure gradient from the problem statement, not because it's any otherwise. And 0 pressure gradient meaning you have just a very simple flat plate. And it's the basis of what we start our analysis. A spear, a missile, or a turbine blade is obviously not 0 pressure gradient, but that's beyond our comprehension. What else can you simplify?
You heard about Z terms because it's 2D?
Yeah, very good. Anything with respect to z, like here, is 0 because of 2D. All right? To the right, steady, 0. What else? What else? W, that's W. That's W, sorry, that's W, UVW, remember? UVW. U, x direction, V, y direction, W, z direction. That's the velocity component. That's all I can do. That's all I can simplify. Okay? Now, if you were trying to get a PhD 50 plus years ago, if you can make a justification and argue with me, and this term is almost 0, you will be granted a PhD. Let me show you why that will help simplify the equation, and I'll come back to justify why that is 0. If you can have the insight to argue that this term is so small compared to the other term in the equations, what left from the Navier-Stokes become no longer nonlinear. The fact that that term disappeared, what's this symbol mu? Anyone remember? Kinematic viscosity was defined as the viscosity divided by density, so I just simplified that. So what left are the two equations now shown in here, continuity, and the simplified momentum of Navier-Stokes by dropping that term that says approximately 0, and I apply the boundary condition. When I'm able to solve this problem, and those are at the wall, no stick, at the edge of the boundary layer, at the infinity, that's infinity. Because the boundary layer has the velocity kept you in the free stream. It turns out with pencil and paper at this stage, the dot, dot, dot require something called the Euler function, which is a mathematical formulation. You take those two equations, 1 and 2, and you can arrange it and look at tables for the solution to this coupled problem, and outcome from those analysis, which I will not go through, these two equations will prevail. And at the end, you will solve for the velocity profile as a function of y. So there's some song and dance here, but those are details that can be basically done by a mathematician, not a fluid mechanicist. So if you follow that step using a table called the error function, you are able to obtain the velocity profile and hence the shear. So that part of it is not important. The important is the physics. Can someone have the insight? And if you have read the handout or read the book, can someone tell me what allowed me to justify folding away this term? I'll give you a hint. I'll give you a hint. I hope someone will see the light and tell me how that can be done. I want you to compare two terms. First term is change of velocity u. U is the velocity in the x direction. Compare that change with respect to x, the streamwise direction. And tell me how would that term, roughly, we'll call it order of magnitude, meaning not the exact number, but just a round of hundreds of thousands of values. Which one is small compared to the other term, and why? Change of velocity u, here. Change of u in the y direction versus change of u in the x direction. Which one you think is much greater than the other? Why? Can you see that? Does that make sense? Remember the car hood problem? The boundary layer is about 5 feet from the hood. Is how big? Anyone remember? Less than 1/10 of an inch versus 5 foot distance. So the rate of change of the velocity in the vertical direction is much, much greater. You know, if this were, say, just for the sake of argument, about 100, this will be in the order of 1. Okay? Yes?
When we say du dx, are we looking at like average?
Kind of average global, yes. Yeah.
Is it going to be different at different?
It's going to be different at different heights, but I'm just looking at it, and this is not an exact analysis. This is only an order of magnitude of, is it 100 or is it 100,000? All right, so it's not looking for the exact decimal accuracy. This is just saying, is this term, if this term were 100, what do you think this term is? And my argument is it's going to be so small, it's going to probably in the neighborhood of 1. And I'm not going to argue, is it 1.2 or 1.1? That's inconsequential. All I'm saying is this is so much smaller than this term. Do you buy that argument? Then Bassi said, if I take the second derivative, which is a function of the first one, this term is going to be even a whole lot smaller, in the sense that if this were 10,000, this may be just 1. Yes?
If it's so small, why not just use like, partial effect of x in the equation?
Say that again. Which equation? Which equation?
In the second equation, why don't we just, if it's so small, why don't we just look like, do udx?
This one.
If it's so small, why not just look like that?
That's a good point. So coming back to this equation, in here, why don't I neglect the other term? Yes?
Because u times that might redeem all of it.
Because the u is order of magnitude greater, much greater than v. You see how it balances?
Yeah.
Very good question. No, it's not trivial. So you want a PhD? That's all you need. Just that simple. That was it. So it's PhD thesis in 1 page. 1 page. And then the equation we still use after more than half a century later. Why here? Why? Questions? So that can be neglected, make the analysis a whole lot easier. Okay, other questions? So I have about 25 minutes left. Yes?
Just one more question on that. So when we have the equations like that, where we have a friction, is that friction coefficient? What is
This one.
that? Yeah.
Mm-hmm. Yeah. How do you get this? Anyone remember?
Du, dy.
Yep, you have to look at the derivative of the gradient right at the wall.
Oh, right at, okay, right
Yes,
at
it is the shear at the wall.
the wall. Oh,
At the wall, that's all you care. That's what you want to estimate. How much friction is generated at the wall. Okay?
So the fact that we have an equation that can be applied
Mm-hmm.
to any scenario, what does that say is similar across the scenarios?
Yeah, it can be applied to any distance, x, from the leading edge of the plate. Yes, correct.
Okay.
Mm-hmm. Yeah. Okay? So I still want you to do the spot evaluation. So what I'm going to do is give you 5 minutes for those who haven't done it. Please do it now, and I'm going to erase the board, and the remaining 20 plus minutes, I want to go through the entire semester recap. Please, okay?